Welcome to solverfy.
For the given problem in a part A, we choose I to be a positive in a smaller cylinder and negative in the larger one. Then we can write a magnetic field is equal to mu naught I R divided by 2 pi C square. This is for the case where R is equal or less than C. Part B, for part B, we have B is equal to mu naught I divided by 2 pi R, where C is greater or equal, C is less than or equal to R, and R is less than or equal to B. For part C, within the larger conductor, we have a superposition of fields due to the current in the inner conductor, plus the field due to the negative current in that part of the outer conductor at the radius less than R. Thus the result will be B is equal to mu naught I 2 pi R minus mu naught I divided by 2 pi R into R square minus B square divided by A square minus B square. This is for the case where B is less than R and R is less than A. If desired, this expression can be simplified to we can write this expression B will be equal to mu naught I divided by 2 pi R A square minus R square divided by A square minus B square. For part D of the problem, outside the coaxial cable, the net current enclosed is 0. So B is equal to 0 for R greater or equal than A. For part E, we test these expressions for one case if A approaches infinity and B approaches infinity, such as A greater than B. Then we have a situation as described in a page 696 of the textbook. Using SI units, the graph of the field is for part F will be, so let's say this horizontal is R and vertical is B. So the graph will spike first, go up and slowly decrease, and then from here it will go down. So for R values are from 0 up to here. In this case, this is 0.018, where it spikes near the top. Here we have is 0.006. This is the magnetic field and this is the R here.